Electric field lines are powerful visual tools that help us understand invisible electric fields. Think of them as imaginary arrows that show us both the direction and strength of electric forces around charged objects. Let's start with the fundamental rule. Electric field lines always point away from positive charges and toward negative charges. This shows us the direction a positive test charge would move if placed in the field. The spacing between field lines tells us about field strength. Where lines are close together, the electric field is strong. Where lines are spread apart, the field is weaker. This is like how contour lines on a map show steep versus gentle slopes. Electric field lines follow 3 important rules. First, they never cross each other. Second, they always start on positive charges and end on negative charges. Third, the density of lines indicates the strength of the field in that region. Now let's see what happens when we have 2 charges of the same type. When both charges are positive, their field lines repel each other, spreading outward and never connecting. The same pattern occurs with 2 negative charges. The situation changes dramatically with opposite charges. When we have a positive and negative charge near each other, the field lines connect directly from the positive to the negative charge. This shows the attractive force between opposite charges. Electric field lines are essential tools for understanding electrostatics. They help us visualize invisible forces, predict how charges will behave, and solve complex problems involving multiple charges. Remember, the lines show direction, their density shows strength, and they reveal the fundamental forces of attraction and repulsion. Understanding electricity starts with 2 fundamental concepts: potential difference and electric current. These work together to make all electrical devices function. Potential difference, also known as voltage, is the work done to move a unit charge from one point to another in an electric field. Think of it as electrical pressure that pushes charges through a circuit. The best way to understand voltage is through a water analogy. Just like water pressure pushes water through pipes, electrical pressure pushes electric charges through wires. Electric current is the flow of electric charges, typically electrons, through a conductor. It's like the flow of water through a pipe. The more charges that flow past a point per second, the higher the current. Here we can see current flowing through a circuit. The electrons move in a directed manner when current flows, unlike their random movement when no current is present. In real circuits, we measure voltage using a voltmeter connected in parallel with the component and current using an ammeter connected in series with the circuit. The key relationship to remember is that voltage causes current to flow. Without voltage, there would be no current. Voltage is the driving force, while current is the result. Here's your key takeaway. Voltage is the electrical pressure that causes current to flow through a circuit. No voltage means no current. Understanding this relationship is fundamental to understanding how all electrical devices work. Electric current doesn't just magically appear in our devices. It needs to be generated from various energy sources. Today we'll explore the 4 main ways we can produce electric current. The first and most common source is chemical energy. Batteries and dry cells convert chemical reactions directly into electrical energy. Inside a battery, chemical reactions create a flow of electrons from the negative terminal to the positive terminal. The second source is mechanical energy. Generators convert motion into electricity. This is how power plants work, whether it's water flowing through a dam, wind turning turbines, or steam spinning generators. The mechanical motion is converted into electrical current. The third source is solar energy. Solar cells, also called photovoltaic cells, convert sunlight directly into electrical energy. When photons from sunlight hit the solar cell, they knock electrons loose, creating a flow of electric current. This is a clean, renewable way to generate electricity. The fourth source is heat energy. Thermocouples generate electricity from temperature differences. When 2 different metals are joined and heated at one end while the other end stays cool, a small electric current is produced. This is used in temperature sensors and some specialized applications. So remember, electric current can be produced from 4 main energy sources: chemical energy in batteries, mechanical energy in generators, solar energy in photovoltaic cells, and heat energy in thermocouples. Each method converts a different form of energy into the electrical energy that powers our modern world. An electric circuit is a closed loop that allows electric current to flow from one point to another. Think of it like a highway system for electricity. The current needs a complete path to travel. There are two main types of electric circuits that we use every day: series circuits and parallel circuits. Each type has unique characteristics that make them useful for different applications. In a series circuit, components are connected one after another in a single path. This means the electric current has only one route to follow, flowing through each component in sequence. In a parallel circuit, components are connected along multiple paths. Each component has its own separate branch, creating multiple routes for the electric current to flow. Now let's compare these two types of circuits side by side. This comparison will help you understand when to use each type and their key differences in real-world applications. Here are the key differences you need to remember. In series circuits, current is the same everywhere, but voltage divides. In parallel circuits, voltage is the same everywhere, but current divides among the branches. Remember these important takeaways. Series circuits have the same current but divided voltage, while parallel circuits have the same voltage but divided current. Most household electrical systems use parallel circuits because if one device fails, the others keep working. Ohm's law is one of the most fundamental relationships in electrical circuits. It connects three essential quantities that determine how electricity behaves in any circuit. The formula is V equals I times R. This simple equation tells us that voltage equals current multiplied by resistance. Let's break down each component. V represents voltage measured in volts, I represents current measured in amperes, and R represents resistance measured in ohms. To understand resistance, imagine water flowing through pipes. Just like a narrow pipe restricts water flow, electrical resistance restricts the flow of electric current. When resistance is high, less current flows through the circuit. When resistance is low, more current can flow freely. The Ohm's law triangle helps us remember how to rearrange the formula. We can solve for voltage, current, or resistance depending on what we know. Let's solve a practical problem. If we have a voltage of 12 volts and a resistance of 4 ohms, what is the current? Using the formula I equals V divided by R, we substitute our values. 12 volts divided by 4 ohms equals 3 amperes. Here's another example. With a voltage of 9 volts and a current of 1.5 amperes, what is the resistance? Using R equals V divided by I, we get 9 volts divided by 1.5 amperes, which equals 6 ohms. In real circuits, we use voltmeters to measure voltage and ammeters to measure current. The voltmeter connects in parallel, while the ammeter connects in series with the component. Remember these key points about Ohm's law. It's the fundamental relationship that governs how voltage, current, and resistance interact in electrical circuits. Master this simple formula, and you'll have the foundation for understanding all electrical circuits. Materials around us can be classified into two main categories based on how they handle electricity: conductors and insulators. Understanding this difference is crucial for electrical safety and circuit design. Conductors are materials that allow electrons to move freely through them. Think of them as highways for electrical current. In conductor atoms, electrons in the outer shell are loosely bound and can move freely from atom to atom. This creates what we call a sea of electrons. Watch how electrons can move easily through the conductor material, creating electrical current. Common conductors include metals like copper wire, silver, and aluminum. These materials are used in electrical wiring because electrons flow through them easily. Insulators are materials that resist or block the flow of electrons. They act like barriers to electrical current. In insulator atoms, electrons are tightly bound to their atoms and cannot move freely. The electrons are held in place by strong atomic forces. Common insulators include rubber, plastic, wood, and glass. These materials are used to protect us from electrical current and to prevent unwanted electrical connections. Here's a helpful comparison showing common examples of conductors and insulators. Notice how metals are typically conductors, while non-metals like rubber and wood are insulators. We can test whether a material is a conductor or insulator using a simple circuit with a battery, light bulb, and the material we want to test. If the material allows current to flow, the light bulb will illuminate, indicating the material is a conductor. If the bulb remains off, the material is an insulator blocking the current. Understanding the difference between conductors and insulators is essential for electrical safety. Conductors carry electricity, while insulators protect us from it. This knowledge helps us use electricity safely in our daily lives. Electric fuses are essential safety devices that protect our electrical circuits and prevent dangerous situations. Think of them as the guardians of our electrical systems. An electric fuse is a simple but crucial safety device. It contains a thin wire or metal strip that is designed to melt when too much current flows through it, breaking the circuit and stopping the dangerous flow of electricity. Here we can see the difference between an intact fuse and a blown fuse. The intact fuse has a continuous metal strip that allows current to flow. When the fuse blows, this strip melts and breaks, creating an open circuit that stops all current flow. Let's see how a fuse protects a circuit. In normal operation, current flows safely through the circuit. The fuse allows this normal current to pass through without any problems. But what happens when there's a short circuit or overcurrent situation? The current suddenly increases to dangerous levels that could damage equipment or cause a fire. This is where the fuse saves the day. When the current exceeds the fuse's rating, the thin wire inside heats up and melts, breaking the circuit and stopping the dangerous current flow. This graph shows exactly how a fuse responds to an overcurrent condition. You can see the normal current, then the sudden spike during a fault, followed by the fuse melting and the current dropping to zero as the circuit opens. Fuses come in many different types and sizes, each designed for specific applications. From tiny surface mount fuses in electronics to large cartridge fuses in industrial equipment, they all serve the same vital purpose of protecting circuits. Remember these key points about electric fuses. They're essential safety devices that protect against dangerous overcurrent conditions. They prevent equipment damage and fires, but must be replaced after they blow. Always use the correct amperage rating, and remember, safety first in all electrical work.